I will talk about the problem 1. The question is um, from lecture notes, collect the definitions and some properties of the some examples of stochastic processes. The first is Poisson process. It is defined by the following properties. First, the number in interval t1 and t2 is a Poisson random variable with a parameter lambda t. And if if two intervals are non-overlapping, then the random variables and the two number of points are independent. And at a time moment, there is no more than one Poisson point. Its probability masses is shown as follows: pxt equals to k, and the expectation of the random process is lambda t, and its autocorrelation is lambda squared t1 t2 plus lambda multiply the mean value of t1 and t2. Its autocovariance is lambda multiplied by mean t1 and t2. And we know the mean of whole Poisson process is lambda t, which is a linear function of t. It matches our common sense. That is, the longer time we wait for, the expected number of buses is larger. The autocorrelation function contains a term mean t1 and t2, which comes from the probability of independent increments. The second is Poisson increment. It is defined as yt equals to xt plus epsilon minus xt divided by epsilon, where xt is the Poisson process, and its probability masses pyt equals to n over epsilon is shown, and its mean is a constant, which is lambda. Its autocorrelation and autocovariance should be separated into two cases. The first is t1 minus t2 absolute value is greater or equal to epsilon. The other is the absolute value of t1 minus t2 is less than epsilon. The Poisson increment process is introduced to prepare us to define Poisson impulse process. We can see that in the expression of autocorrelation RT1 and T2, this term lambda over epsilon minus lambda multiplied by absolute value of T1 minus T2 over epsilon squared, when the absolute value of T1 minus T2 smaller than epsilon represents a triangle with area of lambda, which is independent of epsilon. So when epsilon goes to 0, the triangle becomes an impulse with area lambda. Then we will see the Poisson impulses, which is defined by zt equals to the derivative of xt, where xt is Poisson process. And we can see the mean of the Poisson impulses is constant lambda, and autocorrelation is lambda squared plus lambda delta function t1 minus t2, and the autocovariance is lambda delta function t1 minus t2. So since it's its mean is a constant, we can see that the process zt minus lambda has zero mean, and its autocorrelation should be lambda delta function t1 and t2. So this process is a white noise. And we may define it as the output of a linear time invariant system with the impulse response ht and the input as an Poisson impulse process. Next is the semi-random telegraph signal. It is defined based on Poisson points. The number n of points ti in the interval t1 and t2 of length t is a Poisson random variable with parameter lambda t. It is defined by Pn equals to k equals to e to the power of minus lambda t and lambda t to the power of k divided by k factorial, and where xt equals to 1 if k is even in the interval of 0 and t, and if k is odd in 0 and t, then xt will be minus 1. Then here I show the probability masses of pxt equals to 1 and pxt equals to minus 1. The mean of this process is e to the power of minus 2 lambda t, and autocorrelation, autocovariance are shown as follows. Here we notice that pxt equals to 1 is not a constant. It is not 0.5 because we start with plus 1 here. So it should be a little higher than 0.5. The pxt equals to 1 will only goes to 0.5 if t goes to infinite, which matches our expectation. And here, the expectation of this random process goes to 0 when t goes to infinite, which matches our expectation as well. The autocorrelation goes to 0 when t1 minus t2 goes to infinity. That matches our common sense, because when t1 and t2 are far away, xt1 and xt2 we think they are not correlated. The next is random telegraph signal, which is defined as yt equals to axt, and the probability of a equals to 1 and a equals to minus 1 are both, it should be 0.5 here, and xt is the semi-random telegraph signal. The first order probability masses should be both 0.5, and the mean should be 0. The autocorrelation is e to the power of minus 2 lambda abstract value t1 minus t2, and also the autocovariance. From here, from the probability masses, we may guess that YT may be SSS, and we can also have this sense from the expectation of YT is a constant. The next one is random walk. It is based on a binomial distribution. So, like we may toss a fair coin by n times, and k represent the number of success in the n trials. So the random process is defined as x nt equals to ks minus n minus ks, which is 2k minus n multiplied by s, where s is the length of each step. Here I show the probability masses and mean and autocorrelation, autocovariance. From the probability masses, we guess that when n goes to infinity, this will become a Gaussian density. And the autocorrelation function contains a term of mean T1 and T2, which comes from the probability of independent increments. And the last is Wiener process, which is defined by the limit of xt when t goes to 0 and s squared divided by t goes to alpha and n goes to infinite, where xt is the random walk. Here I show the density function and mean and autocorrelation and autocovariance. We know the Wiener process is characterized by the following properties, including W0 equals to 0 with probability 1, and it has independent increments. It is also a Gaussian increment, and it has continuous passes.